On October 2nd, something fast, incredibly fast, streaked across the Martian sky. An amateur astrophotographer named Stephen Burns noticed it in NASA's raw Perseverance rover images. He created a time lapse, 9 minutes of data compressed, and there it was, moving at 60 kilometers per second against the normal motion of the stars. But here's where it gets really weird. Other users started analyzing the same images, and they claimed to see multiple objects, not just one. Multiple fast-moving anomalies in the October 3rd data, plus a mysterious green flash that nobody can explain. NASA scheduled this observation. Multiple Mars orbiters were supposed to capture the closest images ever taken of an interstellar object. The high-resolution camera capable of 30-kilometer resolution, the ESA's Mars Express, the ExoMars Trace Gas Orbiter, all pointed at 3I/Atlas during its October 3rd flyby. And then silence. No official images, no data release, nothing. Meanwhile, a team at Harvard just published something that's making the entire astronomical community uncomfortable. This object, 3I/Atlas, might have been the source of the famous 1977 WOW signal. The chance of that being coincidence? Just 0.6%. But the WOW signal connection is just the beginning, because 3I/Atlas is breaking every single rule we have for how comets behave. It's producing industrial-grade nickel alloys in space. Its tail points the wrong direction. It's green when it shouldn't be green. And it's following a trajectory so perfectly aligned with our planet that the odds are astronomical. Some are calling it the largest interstellar object ever detected. Others are calling it impossible. Avi Loeb is calling it potentially artificial. And right now it's behind the sun where we can't see it, hidden, approaching its closest point to our star. What happens when it comes back out? Before we dive deeper, if you're finding this fascinating, hit that like button and subscribe so you don't miss what's coming next. Understanding this content is crucial because these scientific findings aren't just cold numbers. They're clues about mysteries of the universe that could completely change our understanding of whether we're alone or not. That's why it's fundamental that you grasp every detail of this content, because each piece of information connects with the next, forming a puzzle that could reveal something extraordinary. Leaving a like helps this video reach more people interested in science and cosmic mysteries. And if you make it to the end of this video, comment Atlas Revealed so I know you followed this entire investigative journey with us. Share with anyone else interested in these space enigmas. Now let's continue this investigation. Let's go back to October 2nd. Stephen Burns wasn't looking for anything extraordinary. He was simply processing the raw image data that NASA makes publicly available from the Perseverance rover. The rover had been instructed to observe the night sky during a specific window, the window when 3I/Atlas was predicted to pass closest to Mars. Closest being a relative term. We're talking about 29 million kilometers of separation. Burns took 9 minutes of consecutive images and stacked them into an animation. In astrophotography, this technique reveals motion that would be invisible in a single frame. Stars appear to move across the frame due to Mars' rotation. But this was different. Something was cutting across that motion at an angle that made no sense for a background star. The speed was the first clue. At 60 kilometers per second, 3I/Atlas moves faster than nearly anything in our solar system. For comparison, Earth orbits the Sun at about 30 kilometers per second. The Parker Solar Probe, humanity's fastest spacecraft, reaches 192 kilometers per second, but only at its closest approach to the Sun. But 3I/Atlas maintains this blistering pace throughout its journey. Burns posted his animation online. Within hours, other amateur astronomers began their own analysis. And that's when someone named Nachtaf, a German username meaning night monkey, made a claim that sent ripples through the observing community. In the pictures from October 3rd, Nachtaf wrote, "You can even see multiple comets. Not one object, multiple." Another user, Alexander Plum, pointed out something else. What is the flash at second 0003 marked with green? Go back and watch Burns's animation frame by frame. There, at the 3-second mark, a brief green luminosity appears. It's not a camera artifact. It's not a cosmic ray hit which would appear as a single bright pixel. This is a diffused glow, localized but distinct. Green light in space has specific causes. On Earth, we associate it with auroras, with copper burning, with certain bioluminescent organisms. In space, green emission typically comes from oxygen or from a molecule called dicarbon, two carbon atoms bonded together. Comets sometimes glow green when solar radiation excites dicarbon in their comas. But here's the problem. Spectroscopic analysis of 3I/Atlas from the Very Large Telescope showed virtually no dicarbon. The object is what astronomers call chain-depleted. It shouldn't be glowing green. Yet photographs from ground-based telescopes in early September clearly showed a green hue developing around the object. The green flash in the Mars images, if real, adds another layer to this mystery. Now, about those multiple objects. This is where things get speculative. But the speculation is coming from people with telescopes and image processing software, not from people making things up. When you stabilize the star field in Burns's animation, when you account for Mars's rotation and the motion of the primary object, there appear to be at least one or two additional points of light moving at different velocities. Could these be imaging artifacts? Absolutely. Could they be background asteroids that just happen to be in the frame? Possibly. Could they be separate fragments, or even smaller objects accompanying 3I/Atlas? That's the question nobody can answer yet, because NASA hasn't released the data. The Mars Reconnaissance Orbiter's HiRISE camera observed 3I/Atlas on October 2nd between 1 and 4 in the morning Mars local time. The ESA's Trace Gas Orbiter and Mars Express both captured observations on October 3rd. These weren't casual snapshots. These were coordinated, pre-planned scientific observations designed to gather the highest resolution data ever obtained of an interstellar object. HiRISE, the High-Resolution Imaging Science Experiment, can resolve features as small as 30 centimeters on Mars's surface from orbit. When pointed at an object 29 million kilometers away, it should still achieve a resolution of about 30 kilometers per pixel. That means if 3I/Atlas has a nucleus 5 kilometers across, as recent estimates suggest, it should appear as a bright cluster of pixels in the HiRISE images. More importantly, HiRISE would be able to distinguish between a single compact nucleus and a fragmented or multi-component object. If there are multiple pieces, if there's a companion object, if there's anything unusual about the structure, we'd see it. So where are the images? NASA's official statement has been minimal. The Mars orbiters successfully conducted their observations. Data is being processed. Updates will be provided as analysis continues. That was over 24 hours ago. In the world of space imaging, 24 hours is plenty of time to at least preview raw data. Some observers have noted that the United States government has been dealing with various administrative issues that have affected the release of scientific data, but ESA operates independently. They should have no such constraints. Yet ESA's images haven't appeared either. The silence feels deliberate. And when official channels go quiet, amateur observers start talking. Because here's what we know for certain. The Perseverance rover did capture something. Multiple amateur analysts examining the same publicly available raw data are seeing anomalies. The object or objects moved at velocities consistent with 3I/Atlas. And there's that green flash that no one can explain. What we don't know is whether those apparent multiple objects are real, whether they're separate from the main comet, and what NASA and ESA saw with their far more powerful instruments. The October 3rd flyby represented the closest any spacecraft has ever come to an active interstellar object. This was our chance to understand what 3I/Atlas really is, to see its structure up close, to determine if it's behaving like a normal comet or like something else entirely. And as we wait for answers, the object itself continues its journey. Right now, it's approaching the Sun, moving deeper into the inner solar system, where Earth-based telescopes lose sight of it against the solar glare. By late October, it will pass behind the Sun from our perspective, completely hidden. And when it emerges in November or December, it will either confirm every natural explanation, or it will have done something that comets simply don't do. There's a pattern in how space agencies handle sensitive observations. When something routine is captured, the data appears within hours. Raw images populate public databases. Press releases get drafted. Scientists tweet their findings. When something unexpected appears, the silence stretches. The technical explanation for the delay centers on data processing pipelines and calibration requirements. Mars orbiters don't transmit images in real time. They store observations on board, then beam them to Earth during scheduled communication windows. From there, the data moves through various processing stages: geometric correction, radiometric calibration, noise filtering. For a typical surface observation, this takes 6 to 12 hours. For a moving target against the starfield, maybe twice that. We're now well past 48 hours since the October 3rd observations. But there's another factor at play, one that doesn't get mentioned in official statements, but filters through the community of researchers who depend on NASA data for their work. Budget constraints and administrative disruptions have created bottlenecks in data release protocols. Not a formal shutdown, but the kind of bureaucratic friction that turns routine processes into delayed ones. Staff working reduced hours, priority systems getting reshuffled, review chains lengthening. ESA operates under different administrative structures, yet their Mars Express and ExoMars Trace Gas Orbiter images haven't appeared either. This suggests either a coordinated decision to withhold preliminary data until full analysis is complete, or technical challenges that both agencies are working through simultaneously. The question becomes, what would be challenging enough to cause this delay? Consider what these instruments were designed to see. The Color and Stereo Surface Imaging System, CASIS, on the Trace Gas Orbiter can resolve features down to about 4.5 meters per pixel when imaging Mars. Pointed at an object 29 million kilometers away, that resolution drops significantly, but the instrument's sensitivity remains high. It's designed to detect subtle color variations in Martian surface materials. If 3I/Atlas was shedding multiple types of ice, if its coma showed compositional variations, if there were structurally distinct regions, CASIS would capture that. Mars Express carries the high-resolution stereo camera, which despite its name focuses on three-dimensional topography. For a distant comet, its stereo capability matters less than its ability to image across multiple wavelengths simultaneously. The camera can distinguish between dust, water ice, carbon dioxide ice, and various minerals based on how they reflect different colors of light. Then there's the Mars Reconnaissance Orbiter's HiRISE, which we've mentioned, but here's what we haven't discussed. HiRISE doesn't just take pictures. It collects data across 3 color bands: blue-green, red, and near-infrared. When pointed at a comet, those bands reveal different aspects of composition and activity. Blue-green light interacts with gases in the coma. Red and near-infrared penetrate through thin dust, revealing structure beneath. If the comet was releasing jets of material from specific locations on its nucleus, if those jets had different compositions, if the brightness varied across the object in ways that suggested a non-uniform surface, HiRISE would document all of it. And here's the thing about sensitive images. They sometimes show features that require consultation before release, not because of conspiracy, but because preliminary observations can be misinterpreted without proper context. If HiRISE captured something that looked unusual, mission scientists would want to rule out instrumental artifacts, cosmic ray hits, or processing errors before making the data public. But while we wait for official channels to open, there's Simeon Schmoss. Schmoss is an astrophotographer who specializes in processing raw planetary data. He's known in the community for his ability to extract signal from noisy images, to stabilize shaky video, to bring out subtle features that initial processing misses. On October 1st, a day before Stephen Burns's October 2nd time-lapse, Perseverance captured a series of night sky images. These were posted to NASA's raw image database, as all Perseverance images are, within hours of being received on Earth. Schmoss downloaded them, applied his processing techniques, and claimed to see an early glimpse of 3I/Atlas in those frames. The claim hasn't been independently verified. The object would have been extremely faint at that distance and angle, but if legitimate, it suggests the comet was detectable even before the main observation window. More intriguingly, Schmoss noted that the motion he detected didn't perfectly match the predicted trajectory. Close, but with a slight deviation. He posted his findings on social media, stating that more analysis was needed, but the preliminary results were intriguing. Then, like the official sources, he went quiet. Whether he's still analyzing, whether he found something he wants to confirm before discussing publicly, or whether he's been asked to hold off, we don't know. What we do know is that there's a gap between what should be routine disclosure and what's actually happening. A gap between the scheduled observations and the data we can examine. A gap that's filled with amateur discoveries, unexplained green flashes, and claims of multiple objects that nobody can officially confirm or deny. The Perseverance rover continues its surface mission. Its cameras remain functional. Its data continues uploading to the public database. But the specific images from those crucial nights, the ones that matter most, are the ones being scrutinized in silence. By October 29th, 3I/Atlas will reach perihelion, its closest approach to the Sun. At that point, it will be entirely behind our star from Earth's perspective, invisible to ground-based telescopes and space-based observatories alike. The window for observation is closing. Whatever NASA and ESA saw, whatever Schmoss found, whatever is happening behind the review processes and data pipelines, the clock is running. Because if there's something unusual about this object, if those multiple points of light are real, if the green flash means something, we need to know before it disappears into solar glare. And if we don't get those answers, we'll have to wait until November when the comet emerges on the other side, potentially changed by its close encounter with the Sun, potentially having done something that natural comets don't do. But there's another reason the timing matters. Because while we've been focused on what the Mars observations might show, Avi Loeb has been looking backward, tracing 3I/Atlas's path, not just through our solar system, but through time. And what he found connects this object to one of the most famous unexplained signals in the history of astronomy. August 15, 1977. Ohio State University's Big Ear Radio Telescope was conducting a routine survey of the sky, searching for signals that might indicate technological civilizations beyond Earth. The telescope operated automatically, scanning narrow bands of radio frequencies, printing out intensity readings on continuous paper. Astronomer Jerry Emmon was reviewing the printouts 3 days later when he noticed something that made him grab a red pen. A signal had appeared, strong and narrowband, lasting exactly 72 seconds. The intensity was so far above background noise that Emmon circled the alphanumeric sequence and wrote one word in the margin: wow. The signal came from the direction of Sagittarius, near the globular cluster M55. It was detected at a frequency of 1420 MHz, which sits within the protected radio astronomy band. No human transmissions are allowed at that frequency. The signal's bandwidth was narrow, less than 10 kHz, exactly what you'd expect from an artificial transmitter rather than a natural astronomical source. The Big Ear never detected it again. Follow-up observations found nothing. For nearly 50 years, the WOW signal has remained one of astronomy's deepest mysteries, until Avi Loeb decided to calculate where 3I/Atlas was on that date. Working backward from the object's current trajectory and velocity, Loeb traced its path through space. In August 1977, 3I/Atlas would have been approximately 600 astronomical units from Earth. That's 600 times the distance between Earth and the Sun, far out in the outer reaches of the solar system, but not yet in true interstellar space. The WOW signal originated from sky coordinates of right ascension 19 hours 25 minutes, declination -27 degrees. These coordinates point towards Sagittarius. Loeb calculated 3I/Atlas's position on August 15, 1977. The object would have been at right ascension 19 hours 21 minutes, declination -19 degrees. For degrees separated in right ascension, 8 degrees in declination. In astronomical terms, that's remarkably close. The chance of two random directions in the sky aligning to within 9 degrees of each other, about 0.6%. But alignment alone doesn't prove causation. Loeb went further. If 3I/Atlas transmitted the WOW signal, how powerful would the transmitter need to be? The signal intensity detected by Big Ear ranged from 54 to 212 Janskis. A Jansky is a unit measuring radio flux density. For comparison, the strongest radio sources in the sky like the Sun or Jupiter typically measure in the hundreds to thousands of Janskis when observed at specific frequencies. At a distance of 600 astronomical units, generating the received intensity would require a transmitter outputting between 0.5 gigawatt and 2 gigawatts of power. That's the output range of a typical nuclear power reactor on Earth. Not impossible, not even particularly advanced by the standards of a civilization capable of interstellar travel, but notable because it's precisely the kind of power budget that would make sense for a deep space probe trying to communicate across vast distances. There's another detail. The WOW signal showed a slight frequency shift. It was detected at 1420.4556 MHz, which is about 10 kHz higher than the neutral hydrogen line frequency. This represents a blue shift, meaning the source was moving toward Earth. 3I/Atlas is moving toward the Sun at approximately 60 kilometers per second. When you account for Earth's motion and geometry in August 1977, the relative velocity would produce a blue shift. Loeb calculated the expected shift. It's close to what was observed, though not a perfect match. The difference could be explained by uncertainties in the exact position and velocity vectors, or by the signal having been transmitted in a specific direction rather than omnidirectionally. Here's where it gets interesting from a strategic standpoint. If you're an intelligence wanting to announce your presence, broadcasting near the hydrogen line makes sense. Hydrogen is the most abundant element in the universe. The 21-centimeter hydrogen line is so fundamental to radio astronomy that any civilization capable of radio technology would monitor it. It's the galactic calling card frequency. The WOW signal lasted 72 seconds because of how the Big Ear telescope operated. It used two feed horns separated in the sky that listened to adjacent regions as Earth's rotation swept them across the target. Each feed horn had a window of 36 seconds. The signal appeared in both horns sequentially, creating the 72-second detection. This means the source was transmitting continuously, or at least for the duration that Big Ear could observe it. Not a brief pulse, but a sustained broadcast. If 3I/Atlas was responsible, this raises immediate questions. Was it a beacon announcing presence to anyone listening? Was it a navigation pulse marking position for some other spacecraft? Was it an attempt at communication, encoding information we lack the sophistication to decode? Or was it entirely unrelated, a cosmic coincidence where an interstellar comet happened to be aligned with a natural radio source we haven't yet identified? The problem is we don't have radio telescope data on 3I/Atlas. Not from August 1977, obviously, but not from now either. No observatory has reported pointing radio dishes at this object. The focus has been on optical observations, on spectroscopy, on imaging. The questions being asked are about composition and structure, not about whether it's transmitting. Loeb is arguing that needs to change immediately. The object is approaching perihelion. It's getting closer to the sun, which means higher temperatures, more activity, more energy available if there's any kind of technological system involved. If it transmitted once at 600 astronomical units, if it's designed to communicate at specific points in its journey, this would be the time. Radio telescopes like the Very Large Array in New Mexico, the Arecibo successor facilities, even the vast arrays in China and Australia could monitor 3I/Atlas across multiple frequencies, not just the hydrogen line, but across the spectrum where artificial signals might appear. The observation would be straightforward. Point, listen, compare to background. Look for any narrowband signals, any modulation patterns, any repetitive structures that natural sources don't produce. If there's nothing, fine. It costs a few hours of telescope time to rule out the hypothesis. But if there's something, if 3I/Atlas is emitting radio signals, even faint ones, even intermittent ones, that changes everything about how we interpret this object. Because a comet doesn't broadcast. A chunk of ice and rock, even from another star system, doesn't generate radio signals at specific frequencies. Natural astronomical sources produce radio emissions, but they're broadband, chaotic, lacking the structure that indicates intention. The WOW signal had structure. It had a narrow bandwidth. It appeared at a meaningful frequency. And if Avi Loeb is right about the alignment, if the 0.6% coincidence is actually causation, then somewhere in the outer solar system 48 years ago, something transmitted a signal powerful enough for us to notice. That something is now racing past Mars, hidden behind the sun from our perspective, doing things that comets aren't supposed to do. The question isn't whether we should be listening. The question is why we aren't already. When comets approach the sun, they begin to shed material from their surfaces. Ice sublimates directly from solid to gas. Dust particles lift off. Trapped volatiles escape. And occasionally, if the comet gets hot enough, trace amounts of metals vaporize from the dust grains embedded in the ice. Nickel and iron appear together in these outgassing plumes, always together because they form together in stellar processes, exist together in meteoritic material, and sublimate at similar temperatures. The ratio varies slightly from comet to comet, but it follows a predictable pattern. For every atom of nickel you detect, you expect to see about 10 atoms of iron. The previous interstellar comet, 2I/Borisov, followed this rule perfectly. Solar system comets follow it. Every icy body we've observed that shows metal emission follows it, except 3I/Atlas. The European Very Large Telescope in Chile has been observing this object with its ultraviolet and visual Echelle spectrograph, an instrument designed to split light into its component wavelengths with extraordinary precision. Between August and September, observers captured spectroscopic data across 6 time periods as the comet moved from 3.14 astronomical units down to 2.14 astronomical units from the sun. In every observation window, nickel emission lines appeared in the spectrum, bright, clear, unmistakable. Iron appeared only when the comet got closer than 2.64 astronomical units. Before that threshold, nickel without iron. After it, nickel with some iron, but in ratios completely unlike anything seen in other comets. The nickel-to-iron ratio measured orders of magnitude higher than solar abundance ratios, higher than typical cometary ratios, higher than natural geologic processes would produce. The production rate made it even stranger. 3I/Atlas was releasing nickel gas at approximately 5 grams per second when first observed. As it got closer and warmed up, that rate increased dramatically. 5 grams per second doesn't sound like much until you consider what it means. That's 430 kilograms per day, over 3 tons of nickel per week, from an object that's supposed to be made primarily of water ice and rock. The surface temperature at 2.8 astronomical units where much of this emission was observed sits far too low to vaporize silicate minerals or metallic grains that would contain nickel and iron. The comet would need to be at least twice as close to the Sun for normal sublimation of refractory materials to occur. Something else is happening. The research team proposed several possibilities. Perhaps nickel exists in a form that releases easily. Nickel tetracarbonyl, a volatile compound, breaks down under ultraviolet light and would release free nickel atoms into the coma. But forming nickel tetracarbonyl requires specific chemistry at specific conditions, specific pathways that aren't common in natural processes. On Earth, we produce nickel tetracarbonyl industrially. It's part of the Mond process used to purify nickel from ore. You heat impure nickel with carbon monoxide at specific temperatures and pressures. The nickel forms gaseous nickel carbonyl. You then decompose it at higher temperatures to deposit pure nickel. The chemical signature of 3I/Atlas releasing nickel without corresponding iron mimics the output of this industrial refining process. There's another possibility the researchers mentioned. Perhaps the nickel is embedded in organic compounds or exists as nanoscale particles that respond differently to solar heating than bulk metal grains. Perhaps photon-stimulated desorption, where light directly kicks atoms off the surface, is somehow preferentially releasing nickel. These are plausible natural mechanisms, complex, requiring specific conditions, but possible. Except here's the thing about natural mechanisms. They leave evidence. They require precursor materials. They depend on the comet's formation history, its journey through space, the radiation environment it experienced. 3I/Atlas likely formed in the Milky Way's thick disk, a region of older, metal-poor stars. Models suggest it spent between 4 and 7 billion years traveling through interstellar space before entering our solar system. During that journey, it would have been exposed to cosmic rays, to background radiation, to collisions with interstellar dust and gas. Could that exposure have created surface chemistry exotic enough to explain the nickel emission? Could the comet have accumulated material during its journey that now, heated by the sun, releases metals in unusual ratios? You'd expect comets that formed around different stars to show chemical differences. Different protoplanetary disks have different compositions. The mix of elements, the ratio of volatiles to refractory materials, the structure of organic molecules. All of this varies based on where and when a solar system forms. But the laws of physics don't change. Nickel and iron still form together in supernovae. They still condense together in protoplanetary disks. They still sublimate at similar temperatures. Getting them to separate, to release in dramatically different ratios, requires overcoming fundamental chemical relationships. Unless the nickel isn't sublimating from ice and rock, unless it's being released through a process that involves chemistry we don't typically associate with comets. Loeb, predictably, has pointed out that the observation matches what you'd expect from artificial nickel production. Not that the comet is a factory, but that if it were a technological object with nickel-based components or a nickel-rich surface coating accumulated during interstellar travel, solar heating could ablate that material. The lack of iron would then simply reflect the composition of whatever is being eroded. The counterargument is straightforward. Why would an advanced civilization build something out of materials that ablate so easily? If you're designing an interstellar probe to last billions of years, you don't use materials that start vaporizing the moment you get near a star. Unless the vaporization is intentional. Unless releasing a plume of material serves some purpose, cooling perhaps, mass shedding to adjust trajectory, signal generation, creating a visible marker that can be observed from a distance. Or unless the coating accumulated during the journey wasn't part of the original design. Interstellar space isn't empty. At 60 kilometers per second, even diffuse gas and dust particles impact with significant energy. Over millions of years, a spacecraft would accumulate surface material just like a comet does. If that material happened to be rich in certain elements based on what regions of the galaxy the object traversed, you might see unusual compositions. The Very Large Telescope data doesn't prove any of this. It simply establishes that 3I/Atlas is behaving anomalously. The nickel without iron, the extreme production rates, the timing of when different emissions appear, none of it fits comfortably into our models of how comets work. And nickel is just one piece. Because while the VLT was documenting metal emissions, the Hubble Space Telescope was capturing images that revealed something even more fundamental, something that challenges the very definition of what a comet is. Comet tails point away from the sun. This is one of the first things you learn about comets. Not because they're following the comet's motion, but because they're being pushed by solar radiation and the solar wind. Photons carry momentum. When billions of photons per second strike dust particles and ionized gas molecules, they transfer that momentum outward, creating the characteristic tail that always streams away from our star. Direction is so fundamental to comet behavior that when astronomers spot a comet, they can immediately determine which way the sun lies just by looking at where the tail points. On July 21st, the Hubble Space Telescope captured the highest resolution image yet obtained of 3I/Atlas. The comet was 277 million miles from Earth, still inbound toward its October perihelion. The image shows a diffuse glow ahead of the object pointing toward the sun. The glow is elongated, roughly 10 times longer than it is wide, forming a teardrop or jet-like structure. Behind the object, in the direction where a tail should be streaming, there's nothing. No bright plume, no extended dust trail, just the faint gradient of scattered light fading into background darkness. The glow is an anti-tail. Now, anti-tails aren't completely unknown in solar system comets. Sometimes under specific geometric conditions, when Earth passes through a comet's orbital plane, we see dust that's been left behind in the comet's orbit, stretching out in front of the comet from our viewing angle. It's an illusion of perspective. But 3I/Atlas isn't in this geometric configuration. The viewing angle doesn't support a perspective effect, and the brightness profile of the forward glow doesn't match what you'd expect from orbital dust. David Jewett, an astronomer at UCLA who led the Hubble observations, analyzed the surface brightness as a function of distance from the nucleus. In a normal comet coma, brightness falls off gradually. Dust spreads out, dilutes, and the intensity drops following a gentle power law. The forward glow of 3I/Atlas drops with a projected power law slope of -3. That corresponds to a three-dimensional emissivity profile with a radial slope of -4. This is steeper than observed in typical solar system comets, much steeper. A steep fall-off suggests that whatever is creating the glow is concentrated near the source and dissipates rapidly. Either the material is extremely fine-grained and quickly pushed away by radiation pressure, or there's active jetting from a specific location on the nucleus creating a directed plume. Jewett's team interpreted this as dust evaporating from the sunward side of the comet. Solar heating would be strongest on the hemisphere facing the sun. Ice sublimates. Dust lifts off. The dust cloud expands forward before radiation pressure begins to push it back. It's a reasonable interpretation, but it requires the comet to be shedding material asymmetrically, with the sunward side dramatically more active than the rest of the surface. That level of asymmetry is unusual, but not impossible. What's harder to explain is the absence of a dust tail. If dust is being lifted off the surface in quantities sufficient to create the visible forward glow, that dust should persist. Radiation pressure would push it outward. The comet's motion would draw it back into a tail, and we should see something. Unless the dust particles are extremely small. Particles smaller than a few hundred nanometers interact so strongly with light that they're blown away from the comet almost immediately, creating a faint haze rather than a distinct tail. But such small particles also get destroyed quickly by solar radiation, breaking down into even smaller fragments until they're essentially invisible. Or unless most of what we're seeing isn't dust at all but gas. Gas doesn't form persistent tails the way dust does. It disperses, thins, becomes transparent once it moves far enough from the nucleus. But if it's primarily gas creating the forward glow, that brings us back to composition questions. What gas? At what rate? And why so concentrated in one direction? There's another possibility that Loeb and his colleague Eric Keto explored in a paper. If 3I/Atlas is generating its own light rather than just reflecting sunlight, the brightness profile would look different. Internal energy sources, whether from radioactive decay or some other process, would create emission that falls off steeply with distance simply because you're moving away from the source. This isn't as wild as it sounds. Some comets show faint air glow in their comas, emission from molecules excited by solar ultraviolet light. But those emissions are well characterized. We know what wavelengths to expect, what intensities, what structures. The Hubble image is broadband. It captures light across a range of wavelengths. Without spectroscopy of that specific forward glow, we can't determine whether it's purely reflected sunlight or includes some emission component. What we can say is that the structure is anomalous. Forward-directed, steep fall-off, no corresponding tail. These features together create a picture that doesn't fit standard comet models without invoking special circumstances. And here's what makes it important. The orientation of this jet or plume, or whatever we're calling it, points in the direction of motion. The comet is traveling toward the sun, and the glow extends ahead in that same direction. If you wanted to design a braking system for an interstellar object, releasing material forward would create thrust in the opposite direction. It's not efficient compared to rocket propulsion, but over long timescales with continuous mass loss, it could produce measurable deceleration. 3I/Atlas has shown no measurable non-gravitational acceleration. Multiple teams have analyzed its trajectory, compiled thousands of positional observations, and found motion consistent with gravity alone. But that analysis has limits. Small accelerations below about 15 meters per day squared would be lost in the noise, and the observation window is relatively short. The comet was only discovered in July. We've tracked it for a few months across a portion of its orbit. If it were decelerating slowly, gradually adjusting its trajectory through directed mass loss, we might not detect it yet. Or the forward jet might be entirely natural, the result of how ice sublimates from a rapidly spinning nucleus with an irregular shape. The image alone can't tell us, but combined with the other anomalies, the nickel emissions, the chemical composition, the trajectory, it adds to a pattern where each individual observation can be explained naturally, but the collective picture becomes increasingly strained. You can have a comet with unusual chemistry. You can have one with an odd trajectory. You can have one that outgasses asymmetrically. But having all of these features in a single object, the third interstellar visitor we've ever detected, starts to push against statistical expectations, especially when you calculate just how massive this thing actually is. When an active comet releases gas and dust, physics demands a response. Action and reaction. Material ejecting from the surface creates thrust. Not much, but measurable. A typical comet might experience non-gravitational acceleration of a few hundred meters per day squared, over weeks and months. This causes the trajectory to deviate from a pure gravitational path. Astronomers use these deviations to estimate how much mass a comet is losing, and by extension, how massive its nucleus must be. More massive objects resist acceleration. A small nucleus shedding material will veer noticeably. A large one barely budges. Between May 15th and September 23rd, 227 observatories worldwide tracked 3I/Atlas. More than 4,000 individual position measurements were compiled at the Minor Planet Center, the International Clearinghouse for Small Body Observations. Richard Cloete, Peter Verres, and Avi Loeb analyzed this dataset. They fitted the observations to a purely gravitational trajectory, calculating where the comet should be at each moment based solely on the sun's gravity and perturbations from planets. Then they looked for deviations. The upper limit on non-gravitational acceleration came out to less than 15 meters per day squared, perhaps much less, perhaps even zero, but certainly below that threshold. This is astonishingly small for an active comet that's visibly outgassing. The James Webb Space Telescope detected carbon dioxide escaping from 3I/Atlas at roughly 150 kilograms per second in early August. That's 13 tons per day. As the comet moved closer to the sun through September, that rate likely increased. When you eject mass at high velocity, conservation of momentum dictates that the remaining object experiences a force. The gas coming off the surface has an outflow velocity around 440 meters per second, measured by Webb spectroscopy. Plug in the numbers, multiply mass loss rate by velocity, divide by the comet's mass. The result tells you how much the comet should accelerate. If 3I/Atlas showed negligible acceleration despite this continuous mass loss, its nucleus must be massive enough that the thrust becomes undetectable in the observational noise. The calculation is straightforward. Given the observed outgassing rates and the upper limit on acceleration, the nucleus must have a mass of at least 33 billion tons. 33 billion tons. That's roughly equivalent to a solid sphere of rock and ice about 5 to 10 kilometers in diameter, depending on assumptions about density and porosity. For comparison, Comet Halley, perhaps the most famous comet in history, has a nucleus about 15 kilometers long and 8 kilometers wide, with an estimated mass of 220 billion tons. So 3I/Atlas, if the mass estimate is correct, would be smaller than Halley, but still substantial. Not the largest comet ever observed, but far from the smallest. And here's where it gets interesting. Before this mass calculation, many astronomers assumed 3I/Atlas was relatively small, perhaps 1 to 2 kilometers across. The brightness seemed consistent with a modest-sized nucleus. The outgassing rates, while notable, didn't scream enormous object. But when you work backward from the lack of non-gravitational acceleration, when you account for how much momentum is being carried away by escaping gas, the numbers demand a much larger nucleus. Unless the nucleus isn't shedding as much material as we think. Unless the observed emissions are coming from a thin active layer covering a much smaller core. Unless something about the structure or composition allows for high outgassing rates without proportional thrust, or unless the object is massive for reasons unrelated to being a large comet. If 3I/Atlas were hollow, if it had internal voids or chambers, if it were structurally more like a spacecraft than a solid chunk of ice and rock, you could have high mass without correspondingly large external dimensions. A metallic shell, even a thin one, would be much denser than ice. A structure built to contain systems, to house equipment, to serve as a vessel, would have mass distributions completely unlike a natural body. Loeb has been careful to present this as one hypothesis among several. The mass could genuinely represent a large comet nucleus. The lack of detectable acceleration could simply mean the object is bigger than initially thought. There's nothing inherently impossible about a 5 to 10 kilometer interstellar comet. We've seen larger objects in our own Oort cloud. But combined with everything else, the nickel emissions, the anti-tail, the wow signal alignment, the chemical anomalies, the mass adds another piece to a puzzle that doesn't quite fit together naturally. Now, before we go any further, I want to make sure you're still with me, because what we're about to discuss gets even more intriguing. If you're enjoying this deep dive into one of the most mysterious objects ever detected, make sure you've hit that subscribe button. This kind of detailed scientific investigation takes time to research and present, and your subscription helps ensure we can keep bringing you this content. Leave a comment below telling me which aspect of 3I/Atlas you find most compelling. The WOW signal connection, the industrial nickel emissions, the mysterious anti-tail, or the Mars observation blackout. And don't forget to like this video. The like button isn't just a metric. It's how YouTube knows to recommend this to other people who are fascinated by space mysteries and cutting-edge science. Now, let's continue, because we need to talk about trajectory and what it might mean. When you plot 3I/Atlas's path through the solar system, something remarkable emerges. The object isn't just passing through. It's following a course that brings it remarkably close to several planets at specific times. On October 3rd, it passed 29 million kilometers from Mars. On November 14th, it will pass about 100 million kilometers from Earth. These aren't impact trajectories, but they're closer than random chance would typically deliver. Loeb and his collaborators calculated what they call the minimum orbital intersection distance, or MOID, for 3I/Atlas relative to each planet. MOID measures the closest theoretical approach between two orbital paths, regardless of where the objects actually are at any given moment. It's a way of asking, if these orbits existed for millions of years, what's the nearest these two paths would ever come? For Mars, the MOID is just 2.7 million kilometers. That's 7 times the Earth-Moon distance. In cosmic terms, that's threading a needle. For Earth, the MOID is larger, but still remarkably small compared to the vast scales of the solar system. Now, here's the critical question. Is this alignment meaningful or coincidental? Interstellar objects enter the solar system from random directions. Their velocities and trajectories depend on where they came from, how they were ejected from their home systems, what gravitational interactions they experienced during their journey. The odds of any particular interstellar object passing close to multiple planets are low, but not impossibly low. We've only detected 3 interstellar objects so far: Oumuamua, 2I/Borisov, and now 3I/Atlas. That's a tiny sample size. We can't yet calculate reliable statistics about what typical interstellar object trajectories look like. But Loeb points out something that can't be ignored. If you wanted to survey the inner solar system, if you were deliberately sending a probe to observe multiple terrestrial planets, you'd choose a trajectory very similar to what 3I/Atlas is following. Close enough to Mars to get detailed observations, close enough to Earth to gather data, timed so that you pass each planet when it's in a convenient position. The geometry isn't perfect. A true optimized trajectory would probably come even closer, would time the encounters more precisely. But for an object that's been traveling for millions of years, for an object entering from a random direction in interstellar space, encountering multiple planets in quick succession is statistically notable. The counterargument is equally straightforward. If billions of comets exist in the interstellar medium between stars, if they're constantly being ejected from planetary systems throughout the galaxy, then over time a certain percentage will randomly pass through our solar system along trajectories that happen to bring them near planets. We notice these objects precisely because they pass close enough to become visible. There's a selection bias. We're not detecting the interstellar objects that pass through the outer solar system far from the Sun, where they remain too faint to observe. So the fact that 3I/Atlas passes relatively close to inner planets might simply mean we're observing one of the detectable ones, not that its trajectory was deliberately chosen. But Loeb takes the analysis further. He calculated what would happen if 3I/Atlas were to maneuver, not claiming it will, but exploring what would be possible if it had propulsion capability. At perihelion on October 29th, the comet will be 202 million kilometers from the Sun, experiencing maximum solar heating, maximum radiation pressure, maximum thermal stress on any structural components. If there were ever a moment to make a trajectory adjustment, this would be it. Solar gravity is strongest at perihelion. A velocity change applied there produces the largest possible alteration to the orbit through what's called the Oberth effect. Spacecraft use this principle routinely. You fire your engines at the point of closest approach to multiply the effectiveness of your thrust. Loeb calculated that a velocity change of 30 to 40 kilometers per second applied during the perihelion passage could redirect 3I/Atlas toward Earth. The object would arrive between late December and early January, intercepting our planet's orbit at a time when we happen to be there. 30 to 40 kilometers per second is enormous. Chemical rockets struggle to achieve even 10 kilometers per second. But if we're discussing technology capable of crossing interstellar space, if we're considering systems that could accelerate an object to 60 kilometers per second through the galaxy, then adjusting velocity by 30 or 40 kilometers per second within a solar system seems plausible. The key question is energy. Where would that energy come from? Solar panels at 1.4 astronomical units would receive significant sunlight, certainly more than at 3 or 4 astronomical units where the object has been cruising. If there were power systems aboard 3I/Atlas designed to harvest solar energy, perihelion would be the optimal charging opportunity. Store energy as the object approaches the sun, then use that energy to power engines during the closest approach. Or if there's a nuclear power source, something based on radioactive decay or fusion, the timing still matters because you want to maneuver when it's most efficient, when the gravitational environment allows your thrust to have maximum effect. Loeb didn't stop there. He considered what would happen to public reaction, to markets, to society if 3I/Atlas were observed maneuvering. The object is currently hidden behind the sun. When it emerges in late November or early December, astronomers will immediately photograph it, calculate its trajectory, compare to predictions. If the orbit hasn't changed, if it's following the path determined by gravity alone, life continues. The object is a comet, perhaps an unusual one, but ultimately natural. If the orbit has changed, if there's evidence of acceleration that can't be explained by outgassing, if the trajectory now points toward Earth or has shifted in ways that indicate intentional control, everything changes. Loeb stated publicly that financial markets could collapse under such news. Not because of immediate physical threat, 3I/Atlas wouldn't arrive until late December even in the maneuver scenario, giving weeks of warning, but because of the implications. Confirmation that we're being visited by artificial objects from other star systems, that something capable of interstellar travel is approaching Earth, that intelligence beyond our own not only exists but is here, would trigger panic, uncertainty, and massive disruption to every system that depends on predictable conditions. Stock markets, currency exchanges, commodity trading, all of these operate on assumptions about the future. When those assumptions are shattered, when the fundamental context of human civilization shifts, value becomes impossible to assess. Do you buy? Do you sell? Do you hoard resources? Do you assume cooperation or conflict? Nobody knows, and in the absence of knowledge, markets freeze or crash. Loeb isn't claiming this will happen. He's pointing out that the possibility exists, that we're in a unique observational window where an object is temporarily out of sight during the exact period when it could make trajectory changes, and that when it reappears, we'll immediately know whether we're dealing with something natural or something else entirely. The scientific community has reacted to Loeb's statements with a mix of interest and skepticism. Some researchers appreciate that he's willing to explore unconventional hypotheses, that he's calculating what would be observable if the artificial hypothesis were correct, providing testable predictions that can either be confirmed or ruled out. Others feel he's overstepping, assigning too much weight to anomalies that likely have natural explanations, publicizing speculative scenarios before sufficient data justifies that level of attention. The debate is healthy. Science progresses through the tension between conservative interpretation and bold hypothesis, between waiting for overwhelming evidence and pursuing provocative ideas that might lead nowhere but occasionally revolutionize understanding. What's undeniable is that 3i/Atlas has generated more discussion, more observation, more analysis than any object since Oumuamua. Telescopes worldwide have tracked it. Multiple spacecraft have imaged it. Spectroscopic campaigns have mapped its composition. And still, clear answers remain elusive. Now, we need to talk about something that might be even more significant than the trajectory, something that could definitively answer whether this is a comet or something designed. We need to talk about rotation and structural integrity. When Stephen Burns first analyzed the Perseverance rover images, when he created that time-lapse showing 3i/Atlas streaking across the Martian sky, he did something else. He examined the raw data for periodic variations in brightness, for patterns that would indicate rotation. Natural bodies tumble. Asteroids, comets, irregular chunks of ice and rock, they spin in complex ways, wobbling and precessing as they move through space. The spin comes from how they formed, from collisions they've experienced, from outgassing events that create torque. A typical comet nucleus rotates with a period anywhere from a few hours to a few days. The exact period depends on size, shape, and history. As the object spins, its brightness varies. When we see a larger cross-section, more sunlight reflects toward us, and it appears brighter. When a smaller cross-section faces us, it dims. By measuring these brightness variations over time, astronomers can determine rotation period, can estimate axis orientation, can even infer basic shape. For 3i/Atlas, multiple teams have attempted this analysis. The challenge is that the object is faint and the coma, the cloud of dust and gas surrounding it, contributes most of the brightness we observe. The nucleus itself, the solid core, is buried within that haze. Separating the nucleus signal from the coma emission requires careful photometry, requires observations over extended periods, requires distinguishing between changes caused by rotation and changes caused by varying activity levels. Recent observations from the Southern African Large Telescope and other facilities measured a rotation period of approximately 16.16 hours. The light curve amplitude, the difference between brightest and dimmest points in the rotation cycle, is about 0.3 magnitudes. That's relatively small. A highly elongated object, something shaped like a cigar or a potato, would show larger amplitude variations. A nearly spherical object would show almost no variation. 3i/Atlas appears to be somewhere in between, suggesting either a moderately elongated shape or a shape that's irregular but not extremely so. Here's where it gets interesting from a structural standpoint. Objects held together purely by gravity, what astronomers call rubble piles, can only spin so fast before they fly apart. The threshold depends on size, density, and internal strength. For a comet-sized body 5 to 10 kilometers across, composed mostly of ice with some rock, the maximum safe rotation period is around 3 to 4 hours. Spin faster than that, and centrifugal force exceeds gravitational binding. The object breaks up, fragments scatter, you're left with a debris field rather than a coherent nucleus. 3i/Atlas rotates with a period of 16 hours, well below the breakup threshold. So from that standpoint, there's nothing unusual. It's spinning at a rate consistent with a gravitationally bound object. But, and this is crucial, if 3i/Atlas isn't held together by gravity, if there's internal structure, if it's something built rather than something that accumulated naturally, then the rotation rate tells us nothing about structural limits. A manufactured object could be designed to withstand much higher spin rates, or could be deliberately spun slowly for stability. The 16-hour period doesn't prove artificial origin, but it also doesn't rule it out. What would rule it out is observing the object break apart, fragment, split into pieces. That would demonstrate structural weakness, would show that it's held together loosely, would strongly support natural comet interpretation. What would support artificial origin is observing controlled changes in rotation. If the spin rate increased or decreased in ways that required torque, if the axis shifted deliberately, if there were any indication of active stabilization, that would be remarkable. We haven't seen that yet. The rotation appears consistent over the observation period, though that period spans only a few months. Long-term monitoring could reveal changes. There's another aspect of rotation that matters: the orientation of the spin axis. This determines which parts of the surface receive maximum solar heating, affects how jets form, influences the appearance of the coma. For 3I/Atlas, the axis orientation hasn't been precisely determined. Different teams have produced different estimates based on light curve modeling and imaging. The uncertainty stems from viewing geometry. We're observing from Earth, which is just one vantage point. To truly map an object's rotation, you need observations from multiple angles, ideally over a full rotation cycle, with high enough resolution to track surface features. For a distant, faint comet surrounded by a coma, that's extremely difficult. The Mars observations might have provided that data. HiRISE, with its high resolution, might have captured enough detail to definitively map rotation and axis orientation. The ESA orbiters, with their multi-wavelength capabilities, might have revealed surface brightness patterns. But we still don't have those images, and the window is closing. Before we dive into what happens next, I need you to do something for me. If you've made it this far, if you're still engaged with this investigation into one of the most mysterious objects ever detected, take a moment right now and leave that like. I know I've already asked, but this is important. The YouTube algorithm needs to see engagement to push this content to more people. And honestly, this level of detailed scientific storytelling takes enormous effort to research and present accurately. Your like directly supports the creation of more content like this. Drop a comment below with your current theory, natural comet with unusual properties, or something more. And tell me what you want to see covered next. Should we dive deeper into the technology that would be required for interstellar travel? Should we explore what other interstellar objects might be out there undetected? Should we look at how governments and space agencies prepare for potential contact scenarios? Let me know in the comments. Now, let's talk about what we're going to see in the next few weeks and what it means. October 29th, perihelion, the closest approach to the Sun. At that moment, 3I/Atlas will be approximately 202 million kilometers from our star, receiving maximum solar flux, heating to its highest temperature. For a comet, this is when activity peaks. Subsurface ices that remained frozen at greater distances warm enough to sublimate. Gas pressure builds beneath the surface crust. That crust cracks or fails, releasing sudden bursts of material. We sometimes see comets dramatically brighten around perihelion, increasing by multiple magnitudes as fresh volatiles are exposed. We sometimes see fragmentation, where thermal stress fractures the nucleus and it splits into two or more pieces that gradually separate. We sometimes see outbursts, sudden explosions of activity that create expanding shells of debris. All of these are natural processes driven by the thermodynamics of ice and the mechanical properties of porous, fragile structures. If 3I/Atlas is a natural comet, we should see at least some of these behaviors. The object should brighten. Its coma should expand. Gas and dust production should increase. The spectroscopic signature should intensify as more molecules are excited by solar ultraviolet radiation. On the other hand, if 3I/Atlas is something else, if it's protected by materials that resist thermal degradation, if it's designed to survive close solar passes, we might see very little change. It might maintain consistent brightness, might show no increase in outgassing, might emerge from perihelion looking essentially identical to how it entered. That would be strange. That would require explanation. How do you build a comet-like object that doesn't respond to heating? You'd need a surface coating, something with high albedo to reflect rather than absorb sunlight, or something with very high thermal conductivity to rapidly distribute heat and avoid hotspots. You'd need to manage subsurface temperatures, possibly through insulation or active cooling. You'd need structural materials that don't crack under thermal expansion. All of this is technically possible. Earth spacecraft that approach the sun use heat shields, reflective materials, and sophisticated thermal management. The Parker Solar Probe survives temperatures exceeding 1,300 degrees Celsius by hiding its instruments behind a carbon composite shield. If a civilization wanted to send a probe through the inner solar system, they'd face similar challenges and presumably develop similar solutions. But here's the thing. We can observe thermal properties remotely. Infrared observations measure how much heat an object emits. By comparing reflected sunlight in visible wavelengths to emitted heat in infrared, we calculate temperature. By monitoring how temperature changes with distance from the sun, we infer thermal inertia, the resistance to temperature change. High thermal inertia means the object heats and cools slowly, suggesting solid, dense materials. Low thermal inertia means it responds quickly to sunlight, suggesting porous, insulating structures. Comets typically have very low thermal inertia. They're fluffy, full of void space, poor conductors. 3I/Atlas has been observed in infrared by several facilities, including NASA's Infrared Telescope facility. The data is still being analyzed, but preliminary reports suggest thermal properties consistent with cometary material. Again, not definitive, but fitting the natural interpretation. However, thermal observations from Earth can only tell us so much. We're looking at the sunlit side, seeing an average over the entire visible surface, observing through the coma which obscures details. Up-close infrared imaging, the kind that Mars orbiters could provide if they had infrared instruments pointed at the right location at the right time, would reveal temperature distributions, hotspots, thermal gradients that would be diagnostic. But we don't have that data either. We're back to waiting, watching, trying to infer from incomplete information what this object really is. Let's talk timelines. October 29th, perihelion. The object is directly behind the sun from Earth's perspective. Ground-based telescopes can't see it. Space telescopes must avoid pointing near the sun to protect their optics. We're blind. The blackout period extends from late October through most of November. Exactly how long depends on the object's brightness and on how close to the sun telescopes dare to point. Conservative estimates suggest 3I/Atlas remains unobservable until late November. By early December, it should emerge from solar glare, visible in the pre-dawn sky as seen from Earth. Observers in the southern hemisphere will have the best views initially, as the object's trajectory carries it through regions of sky more easily visible from southern latitudes. Astrophotographers will capture it first. Amateur astronomers with moderate-sized telescopes will spot the coma, photograph it, measure its position. Within days, professional observatories will target it. Spectroscopy will determine compositional changes. Photometry will measure brightness and activity levels. Imaging will assess whether the structure has changed, whether fragmentation occurred, whether the forward jet remains. And crucially, astrometry will refine the trajectory. Multiple precise position measurements over several nights allow orbit calculation to extraordinary accuracy. Within a week of reemergence, we'll know whether 3I/Atlas is following the predicted gravitational path or whether something has changed. If something has changed, if there's evidence of non-gravitational acceleration that can't be attributed to outgassing, that's when things get very interesting very quickly. Space agencies will convene emergency meetings. Observatories worldwide will drop scheduled programs to focus on 3I/Atlas. Governments will be briefed. And yes, as Loeb suggested, financial markets will react. The scenario isn't science fiction. It's not about invasion or hostile intent. It's simply about confirmation that technological intelligence exists beyond Earth and has sent something to our solar system. That confirmation alone, regardless of any actions taken by the object, regardless of communication or lack thereof, represents the most significant discovery in human history. It means we're not alone. It means interstellar travel is achievable. It means somewhere out there, perhaps many places, civilizations developed, advanced, and reached the stars. The implications cascade through every field. Astrobiology is validated. The search for extraterrestrial intelligence transitions from speculative science to confirmed fact. Philosophy, religion, sociology, every discipline that touches on human meaning and purpose confronts a new reality. And practically, immediately, questions arise. What does it want? Is it observing? Does it carry messages? Will it communicate? Should we try to communicate with it? What if it's not alone? What if there are more coming? These aren't hypothetical questions anymore if 3I/Atlas maneuvers. They become urgent priorities requiring coordinated international response. The United Nations has protocols for this scenario. The Committee on the Peaceful Uses of Outer Space includes provisions for how nations should respond to detection of extraterrestrial intelligence. But protocols written in conference rooms assuming distant radio signals differ enormously from protocols needed for an object actively moving through the inner solar system. Do we track it with military radar? Do we attempt communication with radio transmitters? Do we send spacecraft to intercept it? The fastest rockets we currently have would take months to reach 3I/Atlas. If it's moving away from the Sun after perihelion, the closing speed makes interception nearly impossible with existing technology. We'd be left observing from distance, trying to learn everything we can through remote sensing, wondering whether it will return, whether others will follow, whether this is the beginning of contact or simply a flyby by an automated probe that will vanish back into interstellar space. But let's be clear about probabilities. Most astronomers, most scientists analyzing the data, believe 3I/Atlas is a comet. An unusual comet certainly, one with properties that challenge models and require explanation, but ultimately a natural object following natural physics. The anomalies, the nickel emissions, the forward jet, the trajectory alignment, the wow signal correlation, each has potential natural explanations. And the principle of Occam's razor, that simpler explanations should be preferred unless evidence demands otherwise, favors the comet interpretation. We've observed millions of comets and asteroids. We've seen enormous diversity in their properties. Every time we look closely at a solar system object, we find surprises. The fact that an interstellar comet formed around a different star under different conditions shows even more surprising properties shouldn't be shocking. It should be expected. What would be shocking is if interstellar objects looked identical to solar system objects. They come from different environments, different chemistries, different formation histories. Differences are the baseline, not the anomaly. Where Loeb and others pushing the artificial hypothesis make their case is in the cumulative weight of the anomalies. Yes, each individually can be explained naturally, but all of them together, in the same object, at the same time, following a trajectory that happens to pass close to multiple planets, potentially aligned with a famous unexplained signal from decades ago. That collective picture is what drives continued attention. The counter to that is sample size. We've detected exactly 3 interstellar objects. That's nowhere near enough data to establish what's normal for such objects and what's anomalous. Maybe all interstellar comets emit nickel before iron because of how ices form in different star systems. Maybe forward jets are common in rapidly rotating interstellar bodies. Maybe close planetary approaches happen frequently, and we only notice the objects that pass nearby. With 3 examples, we can't distinguish rare from common, unusual from typical. We need dozens, hundreds of detections before we can say with confidence what interstellar objects normally do. And we're working toward that. The Vera Rubin Observatory, set to begin operations soon, will survey the entire visible sky every few nights. It will detect faint, fast-moving objects that current surveys miss. Estimates suggest it might find several interstellar visitors per year. Over a decade, that's a population large enough to study statistically. We'll see the range of properties, the distribution of compositions, the variety of trajectories. And within that population, we'll identify which objects are genuinely anomalous and which simply represent the natural diversity of material ejected from other planetary systems. Until then, we're working with limited data and high uncertainty. The responsible approach is to investigate thoroughly, to test both natural and artificial hypotheses with equal rigor, and to follow the evidence wherever it leads. That's what's happening now. Multiple research groups are analyzing 3I/Atlas from different perspectives, publishing papers, subjecting findings to peer review, building the body of evidence that will ultimately clarify what this object is. And the timeline for that clarification is relatively short. Between December and January, when the object is observable again, when we have trajectory data, when we can assess changes that occurred around perihelion, the picture will sharpen significantly. If it's just a comet, we'll know. If it's something else, we'll know that too. Now, let me take you deeper into something we haven't fully explored yet, something that might be the most diagnostic property of all. We need to talk about the object's origin, about where it came from, and what that tells us. When astronomers calculate an object's orbit, they don't just determine where it's going. They calculate where it came from. For something moving through the solar system gravitationally bound to the sun, elliptical orbit, that's straightforward. You trace backward in time, following the orbital path, determining where the object was at any historical moment. For an interstellar object, one with hyperbolic trajectory that came from outside the solar system, the calculation is different. You trace the trajectory backward, out beyond the planets, beyond the Kuiper belt, beyond the heliopause where the sun's influence fades and the object was traveling in essentially straight-line motion through interstellar space. The direction that trajectory points, projected onto the celestial sphere, tells you where the object came from. Not necessarily which star it originated around, because stars move and the object has been traveling for potentially millions of years, but the direction it was heading immediately before entering our solar system. For Oumuamua, the first interstellar visitor, that direction pointed roughly toward the constellation Lyra. For 2I/Borisov, the direction pointed toward Cassiopeia. For 3I/Atlas, the calculations are still being refined as more observations improve the orbital determination, but preliminary results point roughly toward Perseus. Here's where it gets intricate. The object is moving at 60 kilometers per second relative to the Sun, but the Sun itself is moving through the galaxy at about 220 kilometers per second. The galaxy as a whole is rotating. Stars orbit the galactic center on timescales of hundreds of millions of years. To determine where 3I/Atlas came from in any absolute sense, you need to account for all of these motions, need to calculate not just the object's velocity relative to the Sun, but its velocity relative to the local standard of rest, the average motion of stars in the solar neighborhood. When you do that calculation for 3I/Atlas, something interesting emerges. Its velocity relative to the local standard of rest is remarkably low. The object is moving at only a few kilometers per second relative to the average stellar motion in our region of the galaxy. For comparison, most stars have velocities relative to the local standard of rest between 20 and 40 kilometers per second. Young stars, recently formed from collapsing gas clouds, have low velocities. Old stars, perturbed by countless gravitational interactions over billions of years, have higher velocities. 3I/Atlas's low velocity suggests it's been traveling for a very long time through relatively undisturbed space. It's not recently ejected from a nearby star system, racing away at high speed. It's drifting, gently moving through the interstellar medium until it happened to encounter the Sun's gravitational field. The age estimate based on this velocity is staggering. Between 4 and 7 billion years of interstellar travel. Older than Earth. Possibly older than the Sun. This is not a young object freshly ejected from a protoplanetary disk. It's ancient. Astrophysical models estimate that trillions of comet-like bodies are ejected into interstellar space over the lifetime of a typical stellar system. Gravitational interactions with giant planets fling comets outward. Some reach escape velocity and leave the system entirely. Those objects then wander the galaxy for eons, occasionally encountering other star systems purely by chance. 3I/Atlas fits this profile perfectly. An ancient comet, ejected from some long-dead stellar system billions of years ago, now just happening to pass through our solar system. Natural, explicable, consistent with theoretical predictions. But here's the alternative interpretation. If you wanted to send a probe to survey star systems, you wouldn't necessarily send it fast. Fast travel requires enormous energy. Moving at relativistic speeds, even 10% light speed, demands energy budgets that would challenge even advanced civilizations. But if you're not in a hurry, if you're thinking on timescales of millions or billions of years, slow travel becomes feasible. Send probes drifting at low velocity. They take ages to reach destinations, but they require minimal energy to accelerate, minimal maintenance, minimal resources. An interstellar probe designed for such a mission would blend into the population of natural interstellar objects. It would move slowly, appear inactive for most of its journey, activate only when approaching a star system where planets might host life. How would you distinguish such a probe from a natural comet? You'd look for exactly the kinds of anomalies we're seeing in 3I/Atlas. Unusual chemistry, structural properties inconsistent with natural fragility, trajectory adjustments, emission signatures that don't match natural processes. The age argument cuts both ways. Yes, the object is ancient, consistent with natural origin. But if it's artificial, that age demonstrates the patience and longevity of whoever built it. A civilization capable of creating systems that function for billions of years, that maintain integrity through the radiation exposure, the micrometeorite impacts, the temperature extremes of interstellar space, that activate appropriately upon detecting a suitable star system. This is the kind of technology that would be required for sustainable interstellar exploration, and if it exists anywhere in the galaxy, this is how it would manifest. We can't yet distinguish these interpretations through observation. Both predict slow-moving objects entering from random directions. Both are consistent with the low velocity relative to local stellar motion. The difference lies in what happens next. A natural comet passes through, outgasses as it nears the sun, and departs. An artificial probe observes, potentially transmits data, potentially maneuvers. That's why the next few months are so critical. We're not just watching a comet. We're running an experiment. We're testing whether this object behaves naturally or exhibits any signature of intent. And there's one more test we need to discuss. One that should already have been performed but hasn't yet, or at least hasn't been reported. We need to search for radio emissions. Avi Loeb has been calling for this publicly. Point-sensitive radio telescopes at 3I/Atlas. Monitor across a wide range of frequencies. Look for any narrowband signals, any modulated emissions, any structured transmissions. If the object is artificial, if it's designed to communicate, if it transmitted the WOW signal 48 years ago, it might still be broadcasting. Even if it's not deliberately signaling Earth, it might be leaking radio emissions. Any electronics generate electromagnetic radiation. Computers, power systems, communication devices all produce radio noise. For human spacecraft, we deliberately shield electronics to prevent interference and unintended emissions. But low-level leakage always occurs. If 3I/Atlas has active systems aboard, if there's any technology operating, radio telescopes might detect the signature. The challenge is sensitivity. The object is far away. currently about 200 million kilometers from Earth. A weak transmitter would be barely detectable even with large radio dishes. But we have large radio dishes. The Very Large Array in New Mexico, the Arecibo Successor Facilities, the Parkes Telescope in Australia, the Meerkat Array in South Africa. Multiple facilities could conduct the observation. It would take hours, perhaps days of telescope time to conduct a thorough search across relevant frequencies. That's expensive in terms of opportunity cost. Every hour spent observing 3I/Atlas is an hour not spent on other research projects. But the potential payoff is extraordinary. If a signal were detected, if 3I/Atlas is broadcasting, that would be confirmation. Immediate, unambiguous confirmation of artificial origin. No natural comet emits narrowband radio signals. Even if the signal were weak, even if it were difficult to interpret, its mere existence would answer the fundamental question. Conversely, if no signal is detected, if multiple facilities with high sensitivity find nothing, that would strongly support the natural interpretation. It wouldn't definitively rule out artificial origin because a probe might not broadcast, might be designed for passive observation, might only transmit on schedules or conditions we don't understand. But it would remove one of the key pieces of evidence for the artificial hypothesis. The WOW signal connection becomes pure coincidence. The object becomes less likely to be technological. Yet, as far as public reports indicate, no major radio observatory has conducted this observation. Why? Possibly because telescope time is competitive and most review committees would reject proposals to search for signals from what appears to be a comet. Possibly because the observation has been done privately and results are pending publication. Possibly because if a signal were detected, authorities would want to understand it, verify it, and decide on communication protocols before public disclosure. This last possibility fuels speculation. Are government agencies monitoring 3I/Atlas with classified assets? Do military or intelligence services have data that hasn't been shared with the scientific community? It's plausible. Governments maintain networks of sensors designed to detect missile launches, satellite movements, and potential threats from space. These systems, if pointed at 3I/Atlas, would generate data. Whether that data shows anything interesting, whether it's being analyzed, whether results would ever be declassified, we don't know. What we do know is that transparency around 3I/Atlas has been mixed. NASA and ESA released some data quickly, spectroscopic measurements, initial images, but delayed or withheld other data. The Mars orbiter high-resolution images, detailed thermal observations. Whether these delays are purely bureaucratic, whether they reflect technical challenges, or whether they indicate uncertainty about how to present unexpected findings remains unclear. We're about halfway through the video now, and if you're still here, thank you. This is complex material, dense with scientific detail, but it matters because we're witnessing something historic. Whether 3I/Atlas turns out to be the most unusual comet ever observed or something far more significant, the investigation happening right now is how science works at its best. Multiple teams analyzing the same object from different angles, publishing results, debating interpretations, testing hypotheses. The process is messy, sometimes contentious, but it's self-correcting. Eventually, the evidence accumulates until consensus emerges. Before we continue, final reminder. Drop that like if you haven't yet. Subscribe if you want to follow this story as it develops, and comment Atlas Revealed if you've made it this far. Your engagement directly supports the channel and helps spread this information to others who care about these profound questions. All right, let's talk about precedent. Let's look at Oumuamua and what we learned from humanity's first confirmed interstellar visitor. October 19, 2017. The Pan-STARRS telescope in Hawaii detected an object moving rapidly through the inner solar system. Its trajectory was immediately recognized as unusual, hyperbolic, coming from interstellar space. The object had already passed closest approach to the sun and was heading outward. By the time astronomers realized what they were seeing, it was already leaving, receding at 26 kilometers per second. Telescopes worldwide scrambled to observe it before it became too faint. Oumuamua, Hawaiian for scout or messenger, exhibited properties that triggered intense debate. Its shape appeared highly elongated, something like 10-to-1 length-to-width ratio, unprecedented for natural solar system objects. Its brightness varied dramatically as it tumbled, consistent with a cigar or pancake-like form. Its surface was extremely red, suggesting organic compounds altered by radiation over millions of years. And most controversially, it experienced non-gravitational acceleration. As Oumuamua moved away from the sun, it deviated from the purely gravitational trajectory. Something was pushing it. The acceleration was small but measurable, and it couldn't be explained by sunlight pressure or comet outgassing because no visible coma was observed. The object showed no signs of releasing gas or dust. Multiple explanations were proposed. Perhaps outgassing was occurring, but the released molecules were transparent at optical wavelengths. Hydrogen, perhaps. Invisible, but still producing thrust. Perhaps Oumuamua was extremely thin, a pancake shape, allowing solar radiation pressure to accelerate it more effectively than expected. Perhaps it was a fragment from a larger body, broken off in a way that left it with unusual properties. Or, Loeb suggested, perhaps it was a light sail, an artificial structure designed to be pushed by starlight, deliberately sent to our solar system by an extraterrestrial civilization. The scientific community largely rejected the artificial hypothesis, not because it was impossible, but because natural explanations, however contrived, seem more probable given our understanding of how common interstellar objects should be. If the galaxy contains trillions of ejected comets and asteroids, we should expect to see them occasionally, and they should sometimes have unusual properties simply due to the diversity of formation conditions. Extraordinary claims require extraordinary evidence, and Oumuamua, while strange, didn't provide definitive proof of technology. The debate highlighted a fundamental challenge in studying interstellar objects. They arrive unannounced, pass through quickly, and leave before we can mount comprehensive observational campaigns. Oumuamua was discovered after perihelion. We only observed it while it was departing. We never saw it approach, never studied it at close range, never had the opportunity to send a spacecraft to intercept it. All our data came from telescopic observations across a few weeks as it rapidly dimmed and vanished. With 2I/Borisov, discovered in August 2019, we had better preparation. Amateur astronomer Gennady Borisov spotted it while it was still incoming, more than a year before its December 2019 perihelion. That gave time to organize observations, to allocate space telescope time, to coordinate international efforts. Borisov turned out to be less controversial. It looked and behaved like a comet. It had a visible coma. It released standard cometary molecules, carbon monoxide, water, cyanogen. Its colors matched solar system comets. Its activity increased as expected when approaching the sun. It experienced non-gravitational acceleration consistent with outgassing thrust. No anomalies demanded exotic explanations. Borisov confirmed that interstellar comets exist and that at least some behave exactly like their solar system counterparts. The lesson from these first two interstellar visitors was that we needed better detection and characterization capabilities. We needed surveys that could spot these objects earlier, while they're still inbound, giving months or years to study them. We needed rapid response programs to immediately target new discoveries with multiple instruments. We needed, ideally, spacecraft capable of intercepting and closely investigating interstellar visitors. That last requirement is technically challenging. Spacecraft take years to design and build. Interstellar objects appear unpredictably and pass through quickly. You can't have an intercept mission ready and waiting. Or can you? Several teams have proposed standby intercept concepts. Keep a spacecraft in Earth orbit, fueled, and ready. When an interesting interstellar object is detected, calculate intercept trajectory, launch immediately. The spacecraft would have limited capability, maybe just a camera and spectrometer, but it could fly close, image the object in detail, sample its coma, transmit data back to Earth. The challenge is cost. Keeping a spacecraft ready, maintaining it in orbit for years waiting for a target, is expensive, and there's no guarantee the target that appears will be accessible. Depending on trajectory, many interstellar objects can't be reached with existing propulsion technology. Still, the proposals exist, and if 3I/Atlas turns out to be as interesting as it appears, funding might materialize for such programs. Because here's the reality. If 3I/Atlas is artificial, if we confirm that, the next interstellar object detected immediately becomes a high-priority target. Is it related? Is it part of a network? Does it behave similarly or differently? We'd want to know immediately. And if that object were accessible, if a spacecraft could reach it, the mission would launch without hesitation. So where does that leave us with 3I/Atlas? We have an object with multiple unusual properties: industrial nickel emissions, forward jet without tail, possible WOW signal connection, close planetary encounters, ancient interstellar origin, massive nucleus, green emissions without dicarbon. Each individually explainable naturally, but collectively creating a pattern that keeps the artificial hypothesis alive. We have a critical observational gap. The highest resolution images from Mars orbiters haven't been released. Radio telescope searches haven't been reported. The object is currently hidden behind the Sun during the period when it experiences maximum heating and could potentially maneuver. And we have a timeline. Late November to early December, the object reemerges. Within days, we'll have updated trajectory data. We'll know if it maneuvered. We'll see how it changed around perihelion. We'll have answers to at least some of the questions that have driven months of speculation. In the meantime, what should we be watching for? First, any early emergence sightings. If the object brightened dramatically around perihelion, if it became much more active, it might become visible sooner than expected. Amateur astronomers with southern hemisphere locations should be scanning the pre-dawn sky in late November. Any confirmed sighting pushes the timeline forward. Second, official data releases. NASA and ESA may publish the Mars orbiter images. Scientific papers analyzing the perihelion passage may appear. These releases often happen with minimal fanfare, just uploads to data archives or submissions to journals, but they would provide crucial information. Third, trajectory updates. The Minor Planet Center continuously refines orbital elements as new observations arrive. When 3I/Atlas is reobserved in December, those updates will indicate whether the orbit changed. Fourth, spectroscopic campaigns. Multiple observatories will target the comet as soon as it's accessible. Within weeks, we'll have new compositional data showing what molecules are present post-perihelion, whether emissions increased or decreased, whether anything fundamental changed about the object's chemistry. And fifth, although less likely to be public immediately, any government or military statements. If classified assets detected something unusual, if there's information not being shared through scientific channels, it might leak or be officially disclosed if deemed significant enough. The next 8 to 12 weeks will determine how 3I/Atlas is remembered. As an unusually interesting comet that expanded our understanding of interstellar chemistry and orbital mechanics, or as the object that changed everything, that confirmed we're not alone, that demonstrated technology can cross the void between stars. Those are vastly different outcomes with vastly different implications. What's your intuition? Having followed this investigation, having seen the evidence for and against the artificial hypothesis, what do you think we're looking at? A comet? A probe? Something in between, maybe a hybrid of natural object and accumulated artificial components? There's no wrong answer at this stage because we genuinely don't know. That uncertainty, that balance between skepticism and openness, is healthy. It's how science progresses into unknown territory. Before we move into the final sections of this investigation, I want to share something that many people don't fully grasp about interstellar space and what it means for objects traveling through it. The distances are incomprehensible. The nearest star to the Sun, Proxima Centauri, is 4.24 light-years away. That means light, traveling at 300,000 kilometers per second, takes 4.24 years to make the journey. At 3I/Atlas's velocity of 60 kilometers per second, that same journey would take over 21,000 years. And Proxima Centauri is our closest neighbor. Most stars are dozens, hundreds, thousands of light-years away. The Milky Way galaxy is 100,000 light-years across. For an object to travel from one side to the other at 60 kilometers per second would take 500 billion years, far longer than the current age of the universe. This is why interstellar travel is so challenging, why even detecting interstellar objects is remarkable. Space is vast beyond human comprehension, and the objects moving through it are tiny, dark, nearly invisible. We only spot interstellar visitors when they pass close enough to the Sun to reflect significant light, when they enter the inner solar system where our telescopes can detect them. For every interstellar object we do detect, thousands, maybe millions pass through the outer solar system unseen. That raises an intriguing possibility. What if 3I/Atlas isn't alone? What if there are other objects accompanying it, traveling in formation, too far separated for us to realize they're related? A fleet of probes, each following slightly different trajectories, each targeting different planets or regions of the solar system. This isn't pure speculation. Some analyses of the Perseverance rover images, the ones showing possible multiple objects, suggest that if those additional points of light are real, they're moving at different velocities than the main comet. Different velocities mean different trajectories. If they're gravitationally bound to 3I/Atlas, if they're fragments or orbiting companions, the velocity differences would be small. But if they're independent objects that happen to arrive at Mars at the same time, that's remarkable. That suggests coordination. That suggests intent. We can't confirm this yet. The data is too noisy, the observations too brief. But it's something to watch for as more observations accumulate. If multiple objects are eventually confirmed, if they're shown to be related but following distinct paths, the artificial hypothesis gains substantial support because nature doesn't coordinate. Random ejections from distant star systems don't produce multiple objects arriving simultaneously unless they fragmented recently from a common parent. And even then they'd follow nearly identical trajectories. Let me take you through a thought experiment. Imagine you're a civilization capable of interstellar exploration. Your technology allows building spacecraft that function for billions of years. Your society thinks on timescales vastly longer than human civilizations, planning centuries or millennia ahead. You want to study other star systems, to catalog planets, to search for life or intelligence. How do you do it? Option 1. Send fast probes. Accelerate to a significant fraction of light speed. Reach target systems in decades or centuries. This requires enormous energy, exotic propulsion, sophisticated shielding against interstellar dust at relativistic velocities. It's expensive even for an advanced civilization. Option 2. Send slow probes. Accelerate to modest velocity, tens of kilometers per second, achievable with nuclear pulse propulsion or ion drives, or even solar sails. The probes take millions of years to reach targets, but energy costs are manageable. You send thousands or millions of probes in all directions. Over deep time, they survey a large volume of the galaxy. Option 3. Hybrid approach. Send slow probes that can replicate. Each probe mines resources from asteroids or comets in the target system, builds copies of itself, launches those copies toward new targets. This is the von Neumann probe concept. Given enough time, a single self-replicating probe could explore the entire galaxy. 3I/Atlas, if artificial, fits option 2. Slow, ancient, passively approaching the solar system, activating only upon arrival. It wouldn't need to carry fuel for deceleration. It could swing through the system, gather data, transmit it back to its origin, and continue into space. Or it could maneuver using locally harvested resources, perhaps breaking apart ice from its own structure or from captured cometary material to create propellant. The energy budget is the key constraint. At 60 kilometers per second, 3I/Atlas has kinetic energy. For a 33 billion ton object, that kinetic energy is substantial. Converting even a small fraction of it into directed thrust could alter the trajectory. But how? Theoretically, a magnetic sail could interact with the solar wind, producing drag or lateral force. An electric sail, a network of charged wires, could deflect solar wind particles. Neither requires carried fuel, both extract momentum from the environment. Have we looked for evidence of such systems? Not specifically, because nobody's been searching for technology. Standard astronomical observations measure brightness, color, spectrum, trajectory. They don't look for artifacts, for structural features, for anomalies that might indicate machinery. That's beginning to change. Loeb's Galileo project is explicitly searching for technological signatures in astronomical data and in Earth's atmosphere. If 3I/Atlas has deployed structures, sails, antennas, panels, high-resolution imaging might reveal them. The Mars orbiter images, if and when released, might show detail sufficient to detect such features if they exist. This brings us to a critical point about scientific investigation. The default assumption is natural origin. That's appropriate. Natural objects vastly outnumber artificial ones. In all of human astronomy, we've discovered countless stars, planets, asteroids, comets, nebulae, galaxies. All natural. We've never confirmed an artificial object from beyond Earth except those we ourselves built. So when encountering something new, assuming it's natural makes sense. The burden of proof falls on those claiming otherwise. But there's a risk to this approach. If we only look for what we expect to find, if our instruments and methods are optimized for natural phenomena, we might miss technological signatures entirely. It's not that scientists would ignore obvious evidence of technology. A radio transmission, a geometric structure, clear signs of machinery would be recognized immediately. But subtle indicators, things that require specifically looking for them to notice, might be overlooked. This is why Loeb's approach, specifically searching for possible artificial signatures even when they're considered unlikely, is valuable. It ensures we're checking, that we're not inadvertently filtering out the most important data because it doesn't fit expected patterns. What would constitute proof? What observation would definitively confirm artificial origin? A radio signal is probably the clearest indicator. Narrowband, modulated, carrying structured information. Natural astrophysical sources don't do that. Maneuvering is another strong indicator. If 3I/Atlas changes trajectory in ways inconsistent with outgassing, if it accelerates perpendicular to the sun's direction or adjusts course to intercept Earth, that requires thrust, requires control. Structural features visible in high-resolution imaging, solar panels, antennas, geometric shapes, surface markings indicating manufacturing. These would be diagnostic. Detection of artificial materials, refined metals, pure elements, alloys with ratios that don't occur naturally, synthetic compounds. 3I/Atlas reemerges in December, when its trajectory is recalculated. When spectroscopy reveals its post-perihelion composition, what do you think we'll find? Natural comet or artificial probe? Comment your prediction below. Here's what we know will happen. The comet reached perihelion on October 29, 2025. It passed just inside Mars' orbit at 1.36 astronomical units from the Sun, experiencing maximum solar heating and radiation. During that time, it was completely hidden behind the Sun from Earth's perspective, invisible to our telescopes, doing whatever it does in the privacy of solar proximity. In early November, it will pass Venus at 0.65 astronomical units. Then in mid-December, it will pass Earth at 1.8 astronomical units, about 270 million kilometers away. Far enough to pose no threat, close enough for excellent observation. By mid-March 2026, it will pass Jupiter at 0.36 astronomical units, receiving a gravitational boost that will slightly alter its trajectory as it exits the solar system. Then it will fade, receding into the darkness, vanishing back into interstellar space from which it came. We'll watch it as long as possible, tracking it until it becomes too faint even for our most powerful telescopes. And then it will be gone, leaving us with whatever data we manage to collect, whatever questions we manage to answer, and inevitably, new mysteries to contemplate. The scientific papers will continue for years. Researchers will analyze the data, model the observations, debate interpretations. Some will conclude definitively that 3I/Atlas was a comet with unusual but ultimately explicable properties. Others will maintain that anomalies remain unexplained, that the artificial hypothesis, while unproven, cannot be conclusively ruled out. And somewhere between those positions, consensus will form about what this object taught us, what it revealed about interstellar chemistry and orbital mechanics, and the diversity of objects wandering the galaxy. But beyond the science, beyond the data and the papers and the debates, 3I/Atlas has accomplished something more fundamental. It's made us look up and wonder. It's reminded us that space isn't empty, that visitors arrive from beyond our solar system, that we share the galaxy with countless objects born around other stars. Some are certainly natural, chunks of ice and rock ejected by gravitational interactions, wandering for eons until chance brings them past another star. But could some be artificial? Could some carry purpose, intent, design? The question matters because it changes how we think about our place in the universe. If we're alone, if intelligence arose only once in this vast galaxy, then we bear enormous responsibility. We're the only witnesses, the only consciousness, the only hope for understanding and preserving and eventually spreading life. But if we're not alone, if others exist or have existed, if technology can cross the stellar void, then we're part of something larger. We're connected to a cosmic community, even if we don't yet know how to communicate with it, even if we're still too primitive to be noticed. 3I/Atlas, whether comet or probe, represents that possibility. It represents the chance, however small, that we're being visited, observed, cataloged by intelligences we can barely imagine. And even if this particular object turns out to be natural, even if every anomaly gets explained, the possibility remains. The next interstellar visitor might be the one that's clearly artificial. The one after that might attempt communication. Somewhere in the steady stream of objects entering our solar system from interstellar space, something designed might eventually appear. And we need to be ready. We need detection systems that can spot these objects early. We need observational protocols that can quickly characterize them. We need analytical frameworks that can distinguish natural from artificial. We need international agreements on how to respond, what to do if we confirm we're being visited. Because the discovery of extraterrestrial technology, even if it's an unmanned probe that departed its home system millions of years ago, even if its builders are long extinct, changes everything. It proves that intelligence is not unique to Earth. It demonstrates that technological civilizations can arise and persist long enough to achieve interstellar capability. It shows that space exploration, even across the immense distances between stars, is possible. and it hints that the galaxy might be filled with such artifacts, scattered across thousands of light years, remnants and representatives of civilizations at various stages of development and decline. Finding even one would be the most significant discovery in human history. It would validate decades of speculation and searching. It would energize space exploration and scientific research. It would provoke questions about origins and meaning and destiny that philosophers and theologians and ordinary people have pondered for millennia. But until that discovery is confirmed, we live with uncertainty. We observe objects like 3I/Atlas. We gather data. We analyze. We debate. We wonder. And we wait for the evidence that will someday, perhaps soon, perhaps in our lifetimes, provide an answer. That waiting is part of the human condition. We've always looked at the stars and wondered what's out there. We've always imagined other worlds, other beings, other forms of life and intelligence. For most of history, that wondering was purely speculative. We had no way to test our ideas, no methods to search for evidence, no realistic hope of ever knowing. But now, in the 21st century, we have those capabilities. We can detect exoplanets around other stars, thousands of them, confirming that planetary systems are common throughout the galaxy. We can analyze the atmospheres of those planets, searching for biosignatures, for signs that life exists beyond Earth. We can listen for radio transmissions, for deliberate signals or unintentional leakage that would indicate technological civilizations. And we can watch for interstellar visitors, for objects that enter our solar system carrying clues about their origin and nature. 3I/Atlas is one such visitor. In the grand scheme, regardless of what it turns out to be, it's a messenger from the depths of space. It formed around another star, in conditions perhaps similar to our solar system, perhaps radically different. It was ejected, sent wandering through the galaxy for billions of years. And it arrived here, now, during the brief moment in cosmic history when humans have developed the technology to detect and study it. That timing is remarkable. A few centuries earlier, 3I/Atlas would have passed through unseen. A few centuries later, assuming we survive and advance, we might have spacecraft that could intercept it, study it up close, even capture samples to return to Earth. But here, now, in 2025, we observe from distance. We use our best telescopes, our most sophisticated instruments, and we extract every bit of information we can. We measure its size, its composition, its trajectory. We watch how it changes as it nears the sun. We look for anomalies that might indicate something beyond natural processes. And we document everything, building a database that future scientists will reference when the next interstellar visitor arrives, and the one after that, creating a catalog of interstellar objects that eventually will reveal patterns and categories and understanding. That's the scientific process. Incremental, cumulative, self-correcting. One observation builds on previous ones. One discovery prompts new questions. One mystery solved reveals deeper mysteries beneath. 3I/Atlas is part of that process. It's not the end of the story, but a chapter in an ongoing investigation of what exists beyond our solar system and whether any of it is looking back at us. So as we conclude this investigation, as we wait for the object to re-emerge from behind the sun, as we anticipate the observations and analyses that will clarify its nature, remember that you're witnessing something historic. Whether this is the moment we confirm we're not alone, or simply the moment we add one more fascinating comet to our catalog, you're here for it. You're informed. You understand the questions, the evidence, the implications. And that matters because science isn't just something done by people in labs and observatories. It's a collective human endeavor. Every person who learns, who understands, who cares about these questions contributes to our species' intellectual and spiritual growth. By watching this video, by following this story, by engaging with these ideas, you're participating in humanity's search for knowledge and meaning. You're part of the investigation. So keep watching the sky. Keep following the news about 3I/Atlas and whatever interstellar visitors come after it. Keep asking questions, keep learning, keep wondering. Because somewhere out there, among the billions of stars in our galaxy, among the trillions of planets that likely exist, there might be others doing the same thing. Others looking up at their skies, wondering if they're alone, searching for signs of intelligence beyond their world. And maybe, just maybe, one of the objects they're observing is from us. Maybe centuries from now, humans will send probes of our own into interstellar space. Maybe our descendants will become the visitors, arriving at distant solar systems, observing worlds we can barely imagine. The future is unwritten. The possibilities are endless. And objects like 3I/Atlas, mysterious visitors from the depths of space, remind us that the universe is stranger and more wonderful than we know, that discovery awaits, that answers exist to questions we're only beginning to ask. Thank you for joining me on this journey through one of the most intriguing astronomical mysteries of our time. If you made it all the way to the end, you're exactly the kind of engaged, curious person this channel exists to reach. Please comment Atlas Revealed right now so I know you completed this entire deep dive. Hit that subscribe button if you haven't already, because we'll be following this story as it develops. When 3I/Atlas reemerges in December, when new data arrives, when papers are published, we'll be here analyzing it, explaining it, exploring what it means. Like this video if you found it valuable. Share it with anyone who loves space science, who appreciates detailed investigation, who wants to understand one of the most significant observations of 2025. Check out the next video that's appearing on your screen right now, where we dive even deeper into related topics. And most importantly, keep looking up, keep questioning, keep exploring, because the universe has mysteries waiting, and some of them might be watching us right back. Until next time, stay curious, stay informed, and remember, whether we're alone in the universe or surrounded by watchers, either answer is extraordinary. We just need the courage to find out which one is true. Thanks for watching, and I'll see you in the next investigation.